Sorry about the rather abrupt interruption. I was borrowing someone else's office, and he came in, so I had to tell him what I was doing in his office. Hopefully today, the guy whose office I'm borrowing today, he's supposedly not here anymore, so hopefully we shouldn't be interrupted again. Okay, so we were talking about these one-way trapdoor functions, and the last thing I wanted to do here was just to talk about this one function that might or might not be a one-way trapdoor function, just to give you an idea of this concept of one-way trapdoor functions. So you might ask whether like squaring integers is a one-way trapdoor function. So if you compute this function, if you try to compute it one way, you might ask, is it hard to compute squares of numbers? Is it hard to take a number and multiply it by itself? This, I hope I can convince you that this is not a hard problem. This is something that can be done pretty efficiently on a calculator, or even by a student in what, 5th, 6th grade on a piece of paper. So this you can do efficiently. What about the other? So that's the one way. That's one way is supposed to be easy, right? So then the question is, then the other way, is that hard? Is it hard to compute squares of integers? Is it hard to compute square roots of integers? So given, for example, this integer 14,641, is it hard to find out which number squared gives that number? And my argument here is that no, this is not too difficult either. One way to approach this is to start out by a good guess. So we know that 100 squared is 10,000. So that's not too bad of a guess to start out with. But it's too small. So we know that the square root of 14,641 should be a little bit bigger. So we try out with 150. But then we get something that's too big. So we try it with something that's in between those numbers we just tried. So 110 squared. That's 12,000, so that's too small, and we continue this way, and in the end we find the square root. So I hope I can convince you that squaring integers is not a one-way trapdoor functions, because both ways are in fact easy to compute. It's easy to compute the square, and it's easy to compute the square root. Well, by easy I mean efficient, and I realize I'm not being very specific about what I mean by efficient. So I hope you will bear with me, but I also hope that you believe me when I say that this is not computationally expensive. Okay. So and something I want you to notice here is that the reason why computing square roots is efficient is because integers have an order, and squaring respects that order. So if I have two integers where one is larger than the other, then when I square them, the same is going to hold true. And we can use that when we compute the square root. When we can use that in order to do this trick, that I showed you, where we compute something, and if it's too big, then we compute something smaller, and so on. So we can adjust our guess and get a better estimate of the square root. So in order to make something that is a one-way trapdoor function, we need to somehow break this order. We need to break this connection between the orders between the sizes, the magnitudes. And one way to do this is through modular arithmetic that I will now introduce. So in cryptography and on computers, computations are often done using modular arithmetic. So ordinary numbers, you can sort of list them. They have an order, and they go on as long as you care to, right? When you compute in modular arithmetic, you decide on a modulus, and then once you reach that modulus, you just start over. So if you're counting modulo 5, there only exists 5 different numbers. And you can see that, once you reach the modulus, you just start over. You can also calculate other modulus, of course. You can calculate modulo 12. And calculating modulo 12, that should remind you of looking at a watch, actually. I mean, if you look at a watch and you want to know how many hours ago did something happen, you can't tell that exactly. You can only tell up to 12, right? There's any multiple of 12 disappears when you're looking at a clock. You don't know how many times the clock went around in between you looking at it. Also calculate modulo 10. If you calculate modulo 10, that's actually the same as just looking at the last digit of the integer, or the smallest digit of the integer. So here, when we're calculating modulo 10, we're only interested in the smallest digit, right? So 11 is just 1, 2, 12 is just 2, and so on. We can calculate modulo 2 if we're only interested in whether the number is even or odd. So a little bit of formal notation. I use this percentage symbol as denoting the remainder of a on division by n. So if I want to calculate a modulo n, I subtract n as many times as possible from a without the solution becoming negative, and that's then a modulo n. So for example, if I want to calculate, I have an example. Okay, so if I want to calculate 15 modulo 6, I subtract 6 from 15 as many times as I can. So 15 minus 6, that's 9. I can still subtract 6 again. So that's 3. And then I can't subtract 6 anymore. So 15 modulo 6 is 3. I will also make another definition. I'll define that A is, I will call this congruent B modulo n, if A and B have the same remainder when divided by n. So I will think of, so when I'm thinking about the numbers modulo n, I'm only thinking about the remainders modulo n, and everything else I'm just ignoring. So for example, if I'm thinking about the numbers modulo 10, remember modulo 10, I'm just interested in the last digit of the number. So modulo 10, I would say that 4 is congruent to, 208,094. Right? And then, so far we've thrown away some of this order, and that's of course nice because now we're moving towards something that can be useful for crypto. But in order to use anything for crypto, we have to have some coherent mathematical rules that we can work with. If everything, we can make any rules we want, but if we're not making rules that make mathematics still work, or if there's some structure to what we're working with, then we can't use it for anything. So we need to make sure that there's some structure to this world that we've invented of modular arithmetic. And what's amazing about modular arithmetic is that actually the mathematics that we're used to with plus and minus and multiplication, they work exactly like we're used to for normal numbers, which is great because then we can just carry that over. Addition is a little bit different and not always possible, but I want to argue that it's essentially the same as what we're used to. We'll get to that. So some examples of math still working is if we're working modulo 10. Remember modulo 10, I'm just interested in the last digit. So imagine I want to calculate this modulo 10. If I just want to know the last digit of this equation, then I can just skip all the other digits because they're not going to have an impact on the last digit of the result. So that's what I do. I throw away everything but the last digit, and then I can calculate this. And that gives me 12. 6 times 2 is 12, and 12 is 2 modulo 10. So the amazing thing about modulus is I can add and then take modulus, or I can take modulus and then add. It doesn't matter. The result is the same, and that's what I mean by math still works. It's the same modulo 2. Imagine that I'm only interested in whether the result of this whether the result of this calculation, whether that's even or odd. Well, if I'm only interested in whether the result is even or odd, well, I can just look at whether each of these numbers are even or odd. And I get this calculation, and 1 times 0 is 0, and plus 0 is still 0. So that means this, if I calculate this, then the result is even. I can also calculate modulo 12. I'm using these examples that I hope will ring a bell to you. That will be easier to understand. So modulo 12, I hope you can also feel, because that's just the clock. So if I'm calculating modulo 12, I might ask what will my clock show 3 hours after it's shown 11? Well, it can't show 14 because that's not on my clock. So what it will show instead is 2. Right. So those were the examples that I hope are most conceptually easy to understand. But of course, this works for any modulo. So it also works modulo 5, for example. So let's say I want to calculate this. I want to calculate this equation modulo 5. Well, what I can do is I can reduce each of the numbers modulo 5 before I calculate it. I mean, if I reduce before I calculate, then that gives you smaller numbers, and that's easier to work with. So that's nice. So this number here is just 1 bigger than a multiple of 5. This one is 3 bigger than a multiple of 5. This one is 4 bigger than a multiple of 5. And then when I calculate 1 times 3 plus 4, that's 7. And 7 is 2 modulo 5. Okay, so I hope this gives you some feeling for how to do calculations while working modulo some number. Okay, and then comes division. Division, it's exactly the same as what you're used to if you think about the stuff that you're used to in a specific way. So I want you to think about the division that you're used to. I want you to think about that as multiplication by the inverse. So if I want to say 4 divided by 3, I want you to think about that as 4 multiplied by the inverse of 3. And with regular numbers, that should be 4 times 1 over 3. Okay, so far so good. I hope you can think about division this way. I want you to make one more mental twist, and that's to think about the inverse of a number as, so the inverse of a, I want you to think about that as the number which multiplied by a gives 1. So the inverse of 3 is 1 over 3 because a third times 3 is 1. Okay. So with these two, with these two ways of thinking about normal division, that generalizes to modular arithmetic. So for example, if we're working modulo 5, we can see that 3 times 2, well, that's 6, which is 1 modulo 5. And this shows us actually that 3 and 2 are inverses of each other modulo 5. Because if I multiply them together, I get 1, so that means they're both inverses of each other. So if I want to work modulo 5 and I want to calculate 4 divided by 3, I should take 4 times the inverse of 3. The inverse of 3 is here 2, and 4 times 2 is 8, and 8 is 3 modulo 5. So 4 divided by 3, if I calculate modulo 5, that's 3. For this, and then I have this final line just to check that it makes sense, because it should, of course, be so that if I first divide by 3 and then multiply by 3 afterwards, I should get back the original number. So it should be so that 4 divided by 3 times 3 should be 4. So let's check if this is true. So 4 divided by 3 times 3, well, 4 divided by 3, we found out before that that's just 3. So 3 times 3 is 9, and 9 is 4 modulo 5. We get back the original number. And this is, of course, not a proof that this will always work, but I hope it sort of makes you feel a little safer about this weird notion of division. Okay, so now I want you to work a little bit with the modular arithmetic on your own. And the exercise that I want you to think about is whether you can always find an inverse modulo any number. So the first exercise, I will start you on that one. So the question is, which of the numbers 2, 3, 4, and 5 have inverses modulo 7? And so there is an efficient algorithm to calculate inverses modulo any number if it exists. But for this exercise, what I want you to do is just check all the possibilities. So the simplest way to do that is make a table of what do you get when you take each of the numbers modulo 7 and multiply them by each other. So in this row I have 0 times, so this is 0 times everything. Here I have 1 times everything. Here I have 2 times, so this is 2 times 0, 2 times 1, 2 times 2, and so on. I hope that makes sense. So now the question is, which of these numbers have an inverse modulo 7? So for which of these does there exist another number I can multiply it with to get 1? Let's just check 2. So I want to check if there's anything that I can multiply 2 by to get a 1. Let's see. There we are. 2 times 4 is 8, which is 1 modulo 7. So 2 has an inverse modulo 7. Okay. So I want you to think about the rest of these numbers modulo 7. Then I want you to do the same modulo 5. And then modulo 10. And then I want you to think a little bit about, like, try to generalize what you've learned and see if you can come up with a rule for when a number has an inverse modulo 10. And finally, think about whether the numbers 0 and 1 have inverses modulo 5. And I rewatched my videos and I saw that actually you can't hear the music that I play. So I'm just gonna sit like this while you pause the video. Bum, 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 da, 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 bum, bum, bum. Okay, I hope you've now paused the video and you're back, that you've tried to do this exercise on your own. And what you should have realized is that 2, 3, and 4, they're like, okay, so all these numbers up here have inverses modulo 7. If we look at 3 times 5 is 15, which is 1 bigger than 14. So 3 and 5 are inverses modulo 7, and 2 and 4 are inverses modulo 7. So they all have inverses. Modulo 5, these numbers also all have inverses. Let me see, 2 and 3 are each other's inverses, because 2 times 3 is 6. 4 is its own inverse, because 4 times 4 is 16. Right. Modulo 10 is a little different, right? Because here they don't all have inverses. And what's happening here is actually that I'm looking, so when I want to see if something has an inverse, I want to see if I can, so let's take 2, for example. So when I want to check if 2 has an inverse modulo 10, I want to check if there's a number which multiplied by 2 gives me a new number that's 1 bigger than a multiple of 10. But any number that's 1 bigger than a multiple of 10 is going to be odd, right? It's like 11, 21, 31, 41. All these numbers that I might hope to hit, they're all odd. However, whichever number I take and I multiply by 2 is always going to be even. So regardless of what number I try to multiply 2 by, the answer is always even, so I can never get 1 modulo 10. So 2 doesn't work. 3 works. 4 again doesn't work because any result is even. The problem for 5 is the same as the problem for 2, but here now every number that I multiply by 5, the result is always going to be divisible by 5, and therefore it's either 0 or 5 modulo 10. Those are the only options. So 5 doesn't work either. And actually, what's happening on a bit larger scale is that 2 and 5 and 4, they have common factors with 10. There's a number that which is greater than 1 that divides both 2 and 10, which is 2. There's a number that's greater than 1 that divides both 4 and 10. And when that happens, then you cannot hit 1 modulo 10. That's the bigger picture, and I'm not sure you need to understand that exactly. You just need to know that that it's not always possible to find these inverses, and it has to do with visibility. It has to do with numbers having common factors. And I hope this even example sort of gave you a feel of what's going on. 0 and 5, do they have inverses modulo 5? Well, 0 doesn't. There's nothing you can multiply 0 with to give 1. 1 does. 1 is its own inverse. 1 times 1 is 1, so therefore 1 has an inverse. Okay. Yeah, that was the end of today, and tomorrow we'll talk more about how to use modular arithmetic for encryption. How do we then build a one-way trapdoor function out of this? And I hope you can already guess that the idea is going to be to square. Well, not exactly square, but yeah, you'll see tomorrow. But it has something to do with the one-way trapdoor function that I showed you, which was not a one-way trapdoor function for integers. Okay, so just to sum up what we've talked about today. We've talked about the very old types of ciphers, and you've seen some examples of ciphers. And as you can imagine, it used to be the only tool that we had available was, pen and paper and the human mind. So that's, of course, what we used for encryption for a long time. The first mechanization of encryption was the Enigma, Second World War encryption system. And after that, I mean, computers have, of course, taken over encryption. Numbers replace letters, bytes replace messages, and this automation means that we can have stronger ciphers because the computers are just more patient and they can compute numbers faster than humans can. It also means that the attack side is stronger as well. So tomorrow we'll talk more about how do we then encrypt now that we have computers available. What I'm hoping that you learned today, I hope you got an introduction to cryptology and when it's needed. I hope that you saw these historic ciphers, the direct substitution and visionaire, and I hope you had some hands-on experience with the attacks. You saw how to represent letters as numbers so computers can work with them. ASCII is one example here. You saw bitwise XOR and how to use that in cryptography. You saw the one-time pad. You saw the stream cipher. And you saw some basic rules of modular arithmetic that we will use tomorrow. And if you had been here, I would have asked if you have any questions. Yeah. Oh, I do have the code book. I have some suggested reading. There's some books that are very good introductions to cryptography. The code book by Simon Singh. I've read that one myself. He's a mathematician, but he describes it. He describes the ciphers very down to earth, but he still like gives you some feel of like the mathematical structure, which I think is amazing. I think he does an extremely good job of making things simple, but still giving you the intuition, the mathematical intuition for what's actually going on. So it's a highly recommended book from my side. The Code Breakers, I've heard that that one's about the same, but I haven't read it myself. And then this is only applicable if you actually have a physical session. So ignore that if you're just here for the. No, maybe if you can, it would be very nice if you go and leave an evaluation actually, if the link is still open when you see this, and just mention in the evaluation that you saw this recording. It'd be very good to know what you think of this as well. Yeah, that was the end. I will see you tomorrow. We'll see if I can turn this off.